Let's just look at our unit objectives again. We have looked at some set theory, our rules of probability. Last lesson we looked at tree diagrams and some probability tables. We're going to come back to some more probability tables, but today we're looking at Venn diagrams, in particular mutually exclusive events, and using the addition rule to solve problems. We've got these last two unit objectives that we haven't covered yet, and we will cover them in the next couple of lessons. So just a quick review on sets and set notation. Now this is review from last year as well as earlier this year when we looked at set notation. That first thing there, the null set or the empty set, is the set with no elements. And we've got Venn diagrams, which we're very familiar with. Our sample space is given by the big rectangle, and any subset of that is a circle. With this one here, which is our most kind of familiar looking Venn diagram, we've got two subsets, A and B, and A and B we can see are both shaded in here, and that represents the union of both of them. The intersection is just that overlap of A and B. The complement, if we look at the Venn diagram here, is all the elements in the sample space that are not in A. Okay, so looking at this Venn diagram, we want to use our set notation to fill in the different bits of our Venn diagram. I'll give you a hint. That first one is A intersection B. I'll get you to pause the video now and just try and fill in those other sections before I give you the answers. So looking at the bit that's just A, this one here, we've got A intersection B prime. It's the intersection of all of A with the complement of B, all of not B. And the same thing over here, we've got the intersection of B and A prime. And the outside bit that's neither A nor B is the intersection of A prime and B prime. We looked at mutually exclusive sets last year as well. If we look at a Venn diagram, this is what mutually exclusive looks like. These sets are disjoint because they have no overlap, i.e. that intersection is the null set. Okay, so let's have a quick look at a worked example. And we've got a sample space here of all the different letters in the word jealousy and two subsets of that sample space. And the question wants us to find the set that represents the complement of A union B. So if we first have a look at A union B, we end up with all of these letters. These are all of the letters that sit in either the set A or the set B or that intersection. And from there, it's really easy to find the complement. The complement's just going to be all the rest of the letters that we haven't looked at yet. So the answer is C. Okay, one more worked example. We want to draw a Venn diagram for this particular situation that we're given, where we've got 110 students completing the VCE, 66 doing maths, 37 doing physics, and 23 doing both. We've got some events defined there, and we just need to draw up our Venn diagram and put some numbers in. So some of them are really simple and we can read them straight off. We've got 110 students in our sample space, 23 sitting in the middle there studying both. 43 study just maths, so we take our math students and we subtract the ones that also do physics, and we've got the same thing over here with physics. 37 do physics, 23 also study maths, so 14 students just study physics. That's not all though, we need to work out how many students do neither, and we want to make sure that everything adds up to 110. So what we need to do is grab our 110, take away all the things that are inside our union, and we're left with 30 students that don't study either maths or physics. Let's work out some probabilities. The kind of key bit of this question is to make sure that you are using that set notation that we came up with before. The numbers are pretty straightforward. If we're looking for a student, the probability that a randomly selected student studies neither of these subjects, we're talking about a student that doesn't study physics and doesn't study maths. And so our notation is going to be M complement intersection P complement. And the numbers are easy. 30 on 110 simplifies down to 3 on 11. Our second one, only studies maths, means studies maths and doesn't study physics. So our set notation is going to be M intersection P prime. And we can read off our Venn diagram, that's 43 on 110. Okay, our addition rule is another one that we looked at last year, and it refers to when we have this situation where there is some sort of intersection of A and B. So they're not disjoint sets, they're not mutually exclusive. From the Venn diagram, we can see that if we want to count up all the things that are in A and B, okay, so our A union B, all we have to do is count up all the things in A, add that on to all the things that are in B, and then we want to subtract the number of things in the intersection. And the reason for that is because if we've counted all the things in A and counted all the things in B, we've counted that intersection twice. So we just need to subtract one lot and we're going to have the union. If we want to find the probability of A union B, all we have to do is go through and divide through by the number of things that are in the sample space. Remember, that's how we always find our probabilities. And our rule tells us that to find the probability of A union B, we get the probability of A, add it onto the probability of B, and subtract the probability of A intersection B. Exactly the same as when we're counting the numbers. So a quick worked example on this. We've got a card chosen at random from a well-shuffled deck. What's the probability that the card is a multiple of 3 or a heart? Okay, so we're looking at the union of those two sets. Let's have a look at what those sets look like. So we've got the event that we choose something with a heart in it, and we've got 13 things in that set. Our second one, a multiple of 3, we've got 12 things in that set. If we want to find the probability of the union between both, what we first need to do is work out the probability of H, probability of T, we've got both of them there. And then we want that intersection. And when we go through and count them up, we've got 3 things that sit in the intersection, 3 things that appear in both of our sets. So our intersection is 3 on 52. I wouldn't simplify any of those, even if you can, because it'll make the maths much easier if they have a common denominator. So if we go through and find our probability using our addition rule, we just need to add the probability of H to the probability of T and then subtract one lot of that intersection. And we end up with 11 on 26. Here is a quick summary of the exercise. You need to have a look at the work plan and complete the questions that are listed there.